So here will be our example on the stationary phase technique. And in fact, in considering this example, you will also become familiar with a very important function. So make sure you read some Wikipedia about it afterwards. And before introducing it, let us write down certain integral. In fact, for the sake of being in certain sense standard, let us introduce factor 1 over 2 pi here. Then, in this case, this defines, for at least some values of the argument, a very famous area function, a quite fundamental one, and this function actually will be one of the main heroes of our course for the remaining weeks. So make sure you familiarize yourself with it. But for now, we are going to evaluate some specific asymptote of this function. And in fact, with our tools, we are ready to consider a limit of negative and large by modulus x. So in fact, in this case, this provides, so to say, the most pedagogical example of the stationary phase. So let us see at this function, which is, say, f of t, and let us see if it acquires some stationary points. So evaluating the first derivative, we find that it reads x plus t squared, and of course, as long as x is negative, as we agreed, this function has two zeros, which are both on the real axis at points plus or minus square root of modulus x. And for simplicity, it's enough actually to split this integration into two domains, which are identical up to complex conjugation. So, and from now on, we will use the following formula. So this has its convenience because on the new integration road, only one of the stationary points is located. So now, as usual, as we can imagine, only the immediate vicinity of the stationary points is important. We need to expand our function f of t in the vicinity of this point. So we write for f of t when t is approximate to square root of modulus x. So for the value of the function itself, we write down. So here are the first and the second contributions, and this in fact becomes minus 2 over 3 modulus x 3 halves. Then this is the value of the function at the extreme at the stationary point itself. Then the first derivative vanishes by construction, and the second derivative at this point just 2 square root of modulus x. Equipped with this understanding, we may write down for the area function the following approximate formula. Again, have in mind that we have large and negative x, so it's 1 over pi, real part. So first of all, as usual, we need to extract the value of the function in the exponential just in the stationary point. And here also goes the integral, which as usual is with integration domain stretching up to infinity. And in the exponential, we have exponent of I times square root of modulus x t squared dt. So now it's time to explicitly evaluate this Gaussian integral, and you are familiar with it from the previous short video. So as a result, this expression becomes, and the integral is just square root of pi over square root of modulus x, and the remaining part is exponent of I pi over 4. So combining everything together, we arrive to the following result. Here we just factored the terms which are explicitly real, and evaluating the real part, we write down, so it becomes just sine of pi over 4 plus 2/3 modulus x. So here's our final result, and please observe that this is very interesting formula, because we just found out that this function defined according to the integral behaves as certain oscillating function, which apart from oscillations, and notice that these oscillations actually have a period which varies with x. It's not simple sine of x, it's sine of some non-trivial power, and on top of these oscillations there is a certain relatively slow decay, and we know its behavior only far from, say, 0. And in fact, of course, there is a whole region of positive x which is not accessible for us for now. Why? Because if you try to solve this equation for positive x, then you immediately realize that there are no stationary points on the real axis, and the evaluation of this asymptote at large positive x is not so straightforward. But very soon you will be equipped with complex plane generalization of this method, and you will find out how actually this function behaves